So that one's going straight to Zoom, so get better quality on Zoom, but this one's really
Okay.
And this is actually a fun stuff.
Oh, thank you.
All right.
You can use this guy to switch.
Please try when you're ready. You can,
Can everyone hear me? Nice and clear. All right. Good morning. First off, of course, thanks to the organizers for giving me the opportunity to give this talk this morning. Just recently, I started my postdoc position at NIST, and I work under Peter Gehring, but the current work that I have presented for you today is work that I did in University of Wisconsin-Madison under my advisor, Chang-Mam Ohm. And this was kind of work that I did in the first couple of years, so it's quite old work, but I'm really happy to kind of represent it today. I never really got to present on this back in the 2017 or 18 when we were working on this. So the entirety of my work in University of Wisconsin was working on piezo-driven magnetoelectric coupling. So of course, with piezoelectricity, you have a material that's able to convert electrical energy into mechanical energy and vice versa. Similarly, with a magnetic material, it can have a magnetostriction, which can then take that mechanical energy and convert it into magnetic anisotropy energy. So with piezo-driven magnetoelectric coupling, I'm trying to use an electric field to generate a lot of strain in my piezoelectric material, and through strain coupling, manipulate the magnetism of a ferromagnetic metal on top. So as I'm showing here, the effect that we wanted to achieve was this 90-degree rotation of in-plane magnetism in the hopes of using it in a like a magnetoresistive tunnel junction for memory devices. So for this to work, you need your piezoelectric material to exhibit anisotropic in-plane strains. If the strain is isotropic in-plane, there's no driving force to rotate this in-plane magnetism. So you really need these anisotropic strains. And for nickel, which is the only metal that we really worked with, it's got a negative magnetostriction. So as I've kind of shown in this schematic, it'll want to align its anisotropy along the more compressive in-plane direction. So our material of choice was this giant piezoelectric lead magnesium niobate lead titanate. And as Lane Martin actually kind of highlighted, it's a solid solution of PMN-PT. And if you choose a composition near a morphotropic phase boundary, you get this flattening of free energy profiles that give competing rhombohedral and tetragonal symmetries. So when you apply an electric field, you can actually have a field-induced phase transition from rhombohedral to tetragonal. And that's where you get these giant electromechanical coupling coefficients and giant piezoelectricity. One thing I want to highlight, though, is in the 001 orientation, when you have rhombohedral polarizations and you rotate them towards the tetragonal phase, you really expect only these isotropic in-plane strains. So back when I first started at Wisconsin, we were limited to this 001 orientation, and you know, it was the only orientation we could grow on silicon. And that's, as I'll show in the next couple of slides, why we had to use silicon. But just keep in mind that in this 001 orientation, you really only expect isotropic in-plane strains. So when using a bulk piezoelectric material, typically what you're doing is you're having your electrodes cover the entire top and bottom surfaces. So that way, when you apply your electric field, you kind of get this unrestricted piezo response involving the whole crystal. And while the strain is large, because of the bulk dimensions, it's going to cost you a lot of voltage to generate the electric field necessary to exhibit the piezoelectric effect. So to reduce that voltage to make it more applicable for memory devices, you really want to work with thin films. And Lane Martin also kind of highlighted that when you have a thin film, even though now you only need maybe single digits of volts to switch the polarization, you find that your strain generation is very much reduced due to this substrate clamping effect. So my entire project at Wisconsin involved removing these films completely from their substrate and recovering that giant piezoelectricity. But I draw the figure this way because when working with thin films, you have to pattern your top electrodes. You can't use the entire top surface because then you'll find a defect somewhere that'll short your capacitor structure. So you find yourself polarizing kind of smaller regions. And I draw the figure this way because there's actually some additional mechanical boundary conditions that result in these membranes. So I'll spare some of the gory details of the fabrication of these membranes, but I'll highlight how we make them freestanding is we would grow these on STO buffered silicon 001 substrates. And then I deposit a platinum electrode on the top so that I can flip it over and attach it to this PDMS and glass soft polymer platform. So I still need stability for handling, but using a xenon difluoride dry etching method, we could completely remove the silicon substrate. And in some samples, you do see a lot of cracking. These membranes are not perfectly stable. They're highly sensitive, but occasionally you can even get some that were completely crack-free, mostly under pretty lucky conditions. And as I'll show on the next slide, I then take these freestanding films, deposit my ferromagnetic nickel, and then I also add an SU8 and gold kind of offset electrode protection layer. And through later fabrication, you do see kind of more cracks arising. So a lot of the challenges were on the fabrication side, but we do this offset gold electrode so that now I can come in with my electrical probe and still leave the nickel kind of free from the probe so that I can measure the magnetic anisotropy. So just briefly, how we did that was we would use the magneto-optic Kerr effect. Just like many other magnetic measurements, you're sweeping a magnetic field and monitoring a hysteresis loop. So if your anisotropy is parallel to the magnetic field, you get an easy axis square loop. And then we hoped to show by applying an electric field along the thickness of the PMN-PT and sweeping a magnetic field, if it rotates 90 degrees, then we can see a hard axis closed loop instead. So rather than rotating the sample to measure different in-plane directions, we want to kind of use voltage to see if we can observe an evolution between these two states. So to begin, it's kind of tricky because I like to plot a lot of these Moch loops all at the same time. And again, we're kind of sensitive to which direction that we're applying the magnetic field. So if you focus on the darkest blue curve, that's our 0 volt state. And if we have the magnetic field at 0 degrees or 90 degrees, it looks more or less unchanged. And if we rotated the other degrees between 0 and 90, we find that we have kind of this easy plane as grown anisotropy in our nickel films. And then as you apply a voltage to get to the lighter blue colors, along 0 degrees, we see a transition from this easy plane anisotropy to a hard axis. And then 90 degrees rotated to that, it even becomes a little bit more square. So what that tells us is our as grown easy plane is then going into a anisotropy where the nickel wants to prefer the short axis of this particular rectangular electrode. And we can kind of continuously induce that anisotropy with the voltage. initially we had used a wet etching procedure that gave us really low yields. So the xenon difluoride etching, which allowed us to have many more electrodes, was actually a very big jump in our productivity. So once I was able to test this on multiple electrodes with other orientations, we found, oh yeah. So again, I just want to highlight in the rhombohedral to tetragonal transition, we should only expect isotropic in-plane strain. So it's kind of a surprise that we see this manipulation at all. But what we found is when we can measure multiple electrodes in different orientations, every single one of them would consistently rotate that anisotropy towards the short axis of the electrode. So this started to give us an idea that the geometry of the electrode was an influencing factor. So to kind of probe this a little bit more, we did finite element method calculations using COMSOL. And what we found was, again, just to kind of skip some of the details, if we plot the differential in-plane strain, it agrees that the more compressive direction would be along the short axis of the electrode. So this is x minus y, meaning that positive x is more tensile, y is more compressive. But we also found that off the electrode area, we would see kind of this other effect where we can get even more strain. So if you kind of plot anisotropy energy with this color bar and the direction of the anisotropy that you would expect are these white lines, you can kind of pattern the nickel both on and off the electrode and see that within the electrode area, you get an easy axis along the short edge of the electrode. But with voltage just off the electrode, you kind of get the opposite effect, which matches pretty well with our COMSOL simulations. We also did this kind of scanning MOC where you can kind of see with the color bar, the strongest effect is right in the center of the electrode. So we rotate slightly off the long axis of the electrode and just show with voltage at 0 volts, we're pretty uniform in our anisotropy, but at 6 volts, we do indeed observe this stronger effect right in the middle. And then just before we started moving on to the 0-1-1 orientation, we started to play with other shapes. And what we found was there's actually an analytical model, it's called the Eshelby tensor, where if you use elliptical electrodes instead of rectangular ones, you can actually make the area within much more uniform in the strain response. But I think honestly, the coolest part to me is you can kind of see a big response just off the electrode, and then it's more of a strain gradient as it gets weaker, the farther from the electrode area. So I guess what I would want to see in a future direction is people utilizing these strain gradients to study effects that rely on a strain gradient. I know that skyrmions, I think, are predicted to translate through strain gradients, and perhaps polar bubbles might as well. So I think if I was to go back and revisit this, I would try to utilize these strain gradients. Otherwise, I just want to acknowledge not all these people contributed to this particular work, but these were people that I collaborated quite heavily with my time in Wisconsin, and of course our funding sources.
Thank you very much. Questions?
The ferroelectric hysteresis.
Well, also, can you explain to me the model of situated thinking about it using this going around?
So the domain state's actually pretty complicated. If I can actually go to do I not have else here? So we did actually do some synchrotron experiments where, where we tried to observe what the domain state was, and as grown, it was pretty, that's not the right button. As grown, it was pretty uniformly rhombohedral with a little bit of monoclinic phase. But as we cycled this voltage, what we're showing is at 0 volts, all the X-ray data is taken. But after various time steps of AC cycling, we could kind of nucleate and grow these tetragonal domains. And then because of the clamping, sort of self-clamping effect, along the edges, it wants to stay more rhombohedral. In the middle, it becomes tetragonal, but certainly not the cleanest in terms of domain structure.
Yes, so thank you for yours. So if I have a problem to so during the fall, we have within some your members of the expected for various different things
Mm-hmm.
So now, you know, this is what happens often in distance. You may have an approach like this school events, but then in practice, the thing to make elements, so you have two different elements externally, so there's a difference on average to track it, and you